an important problem from your previous year exam paper, and this is from Riemann integration, and the problem is using integration by parts so that e to the power x, this can be written as 1 plus x square by factorial 2 to x to the power n by x to the power n by factorial n to infinity. That is, we have to prove the infinite series of e to the power x by using integration by parts. It is given here. Okay. To prove this series, we first start from the integration of e to the power minus t dt, and the range is 0 to x. Okay, and we use here integration by parts. Integration by parts. Okay, so this integration can be integrated by parts as we take this is the first function and 1 is the second function, and the integration is e to the power minus t into integration dt, and the range is 0 to x minus integration the differentiation of, that is ddt of e to the power minus t into integration dt and this, and the range is 0 to x, right? So from this term we get e to the power minus t into t, and the range is 0 to x, and from the second term we get this is plus because the derivative of e to the power minus t, this is minus e to the power minus t, and so this is 0 to x t e to the power minus t dt. Now from the first term we get this is x e to the power minus x, and for the lower integration this is 0 because here t present. Now we use integration by parts successively in the second term, and we get the result as e to the power minus t into t square by 2, the range is 0 to x, we can write this is factorial 2 minus integration e to the power minus t, this is plus, and t square by factorial 2 dt, the range is 0 to x. Okay, and from here we get x e to the power minus x plus x square by factorial 2 e to the power minus x plus, and from here we also get, by integrating by parts, we get x cube by factorial 3 into e to the power minus x plus integration 0 to x e to the power minus t into t cube by factorial 3 into dt. So we use repeated application of integration by parts. This integration can be written as x into e to the power minus x plus x square by factorial 2 into e to the power minus x to x to the power n by n factorial into e to the power minus x plus integration 0 to x to the power n, sorry, this is not x to the power n, it is t to the power n by n factorial into e to the power minus t dt. Okay, now if we integrate the left side, okay, the integration is obviously e to the power minus t and one another minus because of minus t, and the range is 0 to x. So by putting the range we get this integration is 1 minus e to the power minus x. Okay, now we multiply both the portion by e to the power x and get e to the power x minus 1, this is equal to x plus x square by factorial 2 to x to the power n by factorial n plus e to the power x into integration 0 to x t to the power n by n factorial e to the power minus t dt. Okay, we get like this. And if we write 1 in the right side, then we get this line as this is 1 plus x. So we write this term as 1 plus x square by factorial 2 to x to the power n by n factorial plus Rn. Okay, this term looks like the remainder of this series. Here Rn is equal to e to the power x integration 0 to x t to the power n by n factorial into e to the power minus t dt. Okay, here the range of the integration is 0 to x. Okay, that is x greater than equal to 0 here. So e to the power minus t is monotonic decreasing. Okay, and t to the power n is monotonic increasing. Right. Now if we find the supremum of this term in 0 to x, then we get supremum over the interval 0 to x t to the power n into e to the power minus t by n factorial. This is less equal to x to the power n by n factorial, because this is decreasing and this is increasing. Now we write the Rn, that is the remainder term, is less equal to e to the power x into integration 0 to x to the power n by n factorial into dt. Okay, and x to the power n by n factorial, this is constant with respect to t. So we get this is e to the power x to the power n by n factorial into, if we integrate this term, we get one another x here. Okay, because the integration dt, so dt integration is t and the range is 0 to x, so we get another x. Now this is less equal to e to the power x into x to the power n plus 1 by n factorial. Okay, now if we take an, this is equal to x to the power n by n factorial, right? Then an plus 1, this is equal to x to the power n plus 1 by n plus 1 factorial. Then an plus 1 by an, this is given by x by n plus 1, and obviously this is tends to 0. Okay, this is tends to 0, and 0 means less than 1 as n tends to infinity. So by D'Alembert ratio test, we say that D'Alembert ratio test this term x to the power n by n factorial tends to 0 as n tends to infinity, or this is convergent as n tends to infinity. So we, using this result, we say that Rn tends to 0 as n tends to infinity. Okay, now in the series of e to the power x, the remainder term Rn tends to 0 as n tends to infinity. So we can expand e to the power x as an infinite series, and the infinite series looks like e to the power x This is equal to 1 plus x square by factorial 2 plus x to the power n by n factorial to infinity. Okay, and this is our proof of this problem. Okay, and we expand this series or expand e to the power x only by using integration by parts. Okay, this is very interesting and important problem. Thank you for watching.